All right, good morning. This short video is on sizing pipe for heat transfer, in particular, sizing pipe for laminar or turbulent flow. So, something that a lot of, is involved in heat transfer a lot is saying, hey, what pipe diameter am I going to choose? So this is some 3/4 inch copper pipe, and if I had some flow that I wanted to go through, would the flow actually be laminar or turbulent? A really important skill that we want you to have, and you should have if you go out and do anything with thermal fluids type work. Flow going through, laminar or turbulent. So going away from the pipe and giving an image from it, okay, what we would like to be able to do is answer that question for a situation like this where we have some fluid coming in. This might be, say, be water, 40-degree water at 5 GPM. This might represent a pump that's getting that water flowing, and it's going through a tube, and for some reason maybe the surface temperature of the fluid is 100 degrees Fahrenheit. Maybe we're trying to heat up the fluid, okay? Or maybe this fluid is on this piping is on top of a roof, and this is chilled water going through our building. Okay? I'd like to be able to say, hey, if I want this flow to be laminar, how big does that pipe need to be? And if I want it to be turbulent, how big should it be? Now the short answer is, if you want to be turbulent, you should take this flow and try to squeeze it through a really small diameter pipe, and then the flow is going to tend to be turbulent. On the other hand, if you want it to be laminar, nice smooth flow going through, maybe you want to avoid a lot of pumping energy. You want to make that pipe bigger. So bigger pipe, more likely laminar, less pumping energy. Small pipe, more likely turbulent, more pumping energy. Okay, well, how actually to come up with that for a certain flow, like 5 GPM water, 40 degrees Fahrenheit, how to come up with a sense of whether it's going to be laminar or turbulent. So the first thing is to talk a little bit about the motion of the particles when they actually go through. Say if these are water molecules and they're going through there, are they moving in a straight line? Okay, are they flowing upwards, downwards to the exterior? Are they flowing in some sort of random swirling type pattern? Basic idea to start with, we still have the no slip condition. So when we did convection earlier in the semester, we had a fluid flowing over a plate, and at the surface of that plate there was absolutely no motion. So there was an area, which sometimes is called a film, where the fluid is just stationary. Okay, and then in the middle the fluid is actually moving. So stationary out at the edge, no slip condition, moving in the middle. Okay, that's the first idea. Okay. The second idea is our boundary layer. So talking about that a little bit, when we did flat plate flow over a flat plate, and we had some fluid actually approaching, okay, there was a no slip condition all the way along, but the amount of fluid that got affected by friction started increasing in height, and so we got a boundary layer, and our symbol for that was the boundary layer thickness was a Greek delta. Okay, well, how does it look for a pipe? A pipe's a little bit different because we have the fluid completely surrounded. All the fluid, not just the fluid, say, like at the bottom, is ended up being affected by friction. So how does it look like? What does it look like? Well, there's a figure in your book I asked you to look at, and I got a duplication of that figure for us to take a look at it for just a second. So this is kind of like a classic picture of what is going on. So over here on this side is the fluid entering the pipe, and it has a uniform velocity. It's moving along this uniform velocity. And here they show the boundary layer, and just like with a plate, the boundary layer gets thicker and thicker and thicker, but different from a plate is the two boundary layers end up meeting, and then you just have a region where all the fluid is affected by the frictional effects with the wall. So a little bit different case, actually. We're not going to have to worry about the thickness of the boundary layer increasing as we go through our pipe. Instead, for a complete analysis, we say, hey, there's an entry region where the boundary layer is developing, and then there's a fully developed region where there's just essentially no boundary layer. The pipe, all the fluid is actually affected. All right, so if you go on and get into details on fluids and heat transfer and pumping requirement through pipe, you will study this entrance length, okay? Many times it's short, and for many applications it's not a huge part of the analysis, and we can understand what's going on by just doing the fully developed flow. ME126, that's what we're going to do, fully developed flow. All right, so in some ideas, no slip condition, developing boundary layer, but eventually we just have completely developed flow where all fluid is affected somewhat by the friction at the wall of the pipe. Okay, last thing is, what about the pipes? What about the speed actually of the fluid? Regardless of whether it's turbulent or laminar, we get this effect where we have this fluid coming in. This is sometimes called a bell mouth, an entrance area. And let's say it comes in at a uniform flow. Well, the stuff at the edge ends up sticking. And one way of thinking about it is the fluid that came in, because there's this layer at the edge where the fluid can't move, there's less area for it to actually flow through than the area at the entrance because of that sticking. So as a consequence, the fluid, in order to maintain continuity, in other words, mass in is equal to mass out, the fluid in the middle needs to speed up. Okay? And that's what this diagram is showing. Virtually no speed at the edges, faster in the middle. Okay, so that is our first step, some basic understanding about nature of flow. And we're going to just take a look at the fully developed region and start working on laminar or turbulent. Okay. And what do those look like? What is the motion of the molecules look like in laminar versus turbulent? So give me just a second here. Okay, so this is supposed to represent a cross-section of pipe where I have fluid going through, and let's say it's fully developed in here. What does laminar look like? Well, two ideas on it, or two synonyms. One is smooth and the other is layered. So with laminar flow, it's smooth, and secondly, we have flows in layers that are essentially slipping past each other. So we have a bottom layer here that's not moving very much because it's actually near the wall. We have up here, we have the exact same conditions. Furthermore, in the middle, it's a little bit faster, and then all the way in the middle, it's fastest. And so we would have laminar flow depicted this way, with this layer moving smoothly, this layer above here moving a little bit fast, this layer here moving fastest. No mixing, okay? No particles that are actually going from the middle and then going down to the edge and back, okay? How is this for actually convective heat transfer? Heat transfer, say, from a pipe into a fluid, okay? Heat transfer from a pipe into a fluid. Well, turns out this is pretty poor. Convection is a combination of conduction into the fluid plus heat being carried away by the fluid to some fluid that's actually, say, in the middle of the pipe, right? In this case, there's none of that upward motion, or virtually hardly any of that upward motion, so as a consequence, the heat transfer is mostly by conduction through the fluid. All right, turbulent, swirling flow, okay, swirling flow. So that's easy enough to see. You get a lot of detail into it, okay. But basically, any particle that's going through any fluid particle that's going through this section of pipe is not going to move in a straight line. It is going to move in some sort of swirling pattern, and that's going to include sometimes where it goes down to the wall, picks up heat, can deposit that heat to other particles or mix with other particles, and go back and do it again. Okay, so it's not necessarily like a sinusoidal up-down pattern, but the main point is that their particles are moving about, sometimes come into contact with the wall, pick up heat, deposit that heat. This is great for convective heat transfer. All right, so that is good enough to give you a little bit of feel for what's going on with the different types of fluid motion. Sticking at the edge, either laminar flow or swirling flow, and we're going to stick an ME126 with fully developed flow. All right, the next thing then is how to decide whether laminar or fluid, laminar or turbulent or not turbulent, and that is going to be our Reynolds number. So coming up with a formula for a Reynolds number. Right. If you look in the book or your FE review material, they're going to have this symbol, RED. D stands for diameter, and that tells you that we're doing internal flow inside of tube. Okay, so what's going to make it more likely that fluid is going to be, its flow regime within a tube is going to be turbulent? Okay, well, let me list some factors and we'll just go through them one by one. Okay. All right, so actually, we can go through all these factors, but just what they mean. This would be the density of the fluid. This would be the fluid's average velocity. This would be the pipe inner diameter. This is the fluid's viscosity, and here's the mass flow rate. All right. Well, in short, probably the main ones to think about are these three terms here. Okay. The smaller the pipe diameter, the more fluid the fluid has to squeeze through a small area, and those frictional effects are very, very large and can result in turbulence. Viscosity can be thought of in a sense as attraction of fluids or cohesion of fluids to adjacent molecules. And if a fluid's going to be doing some sort of random flow, that means the adjacent molecules are not exerting much of a cohesion with it, and therefore it is more likely to be, it can be turbulent. So low viscosity, more likely turbulent; high viscosity, more likely laminar. Okay? And then finally, our mass flow rate. Well, the more mass we're trying to put through a small tube, so here's our tube entrance, the more mass we try to squeeze in there, the greater those frictional effects, and the more likely it's going to be turbulent. Hang on for a second, please.